So welcome. So last time we were doing about waves, and we got to the stage where we developed two equations. One equation told me what the y-axis displacement is at some given x position and at some given time in the future. So basically you go from this and you go down here, and now your y-axis displacement is that because you've not only gone to the position x, but you've gone to the time. You've gone to the time. So that's t seconds and that's 0 seconds. So it's an equation which has two variables in it, and we had two forms for it. We had basically the linear form, which I find actually the more complicated of the two, but it's basically the amplitude modified by a sine function. And the sine function is basically the ratio of your position and the wavelength multiplied by 2 pi to get into radians. And then you have the ratio of the distance caused by the time passage ratio to your wavelength multiplied by 2 pi to make it radians. When you break it down, that's what it's really doing. And we have the negative sign there because for the most part, and certainly here, I'm talking about a wave which is traveling to the right. If it was traveling to the left, then that would be a positive. And the justification for that is when you're stepping out into traffic and you want to know what's going to happen in the future, you'll look at the cars that are coming to you. So if the wave is traveling to the right and you want to know what's going to happen in the future, look to your left. And the future is what you're trying to calculate. So you look to the left by doing a negative sign. And then we have what actually looks, at first glance, it's very uncomfortable because it's new definitions to us, but get used to the definitions. And we have y equals a sine kx minus omega t, where k is the angular wave number and omega is the angular frequency. And you multiply the angular wave number by a position, a displacement, a distance along the line, and you multiply your angular frequency by a time interval. And we tend to use this a fair amount, actually. And I think what we said down here, just so that you know. So this is what happens if we don't start off just as we're supposed to. We don't start off and have this vision of our wave at time t equals 0. Suppose we start off and we're a little bit early so that we actually have that. We started a little bit too soon. We started down here when the clock was not reading 0. How can we deal with that? And the way we deal with that is we include a phase angle. We recognize that that's just a little bit of a wave. That time interval is just a little bit of a wave. And I can express that as a little bit of an angle because of the circular motion link. So I say a sine kx minus omega t plus this phase angle. And the phase angle will be so many radians. So if it was half a wavelength out of phase, it would be pi radians. If it was a quarter of a wavelength out of phase, it would be pi over 2. If it was 1/17 of a wavelength, it would be 2 pi over 17 radians. 2 pi divided by whatever the fraction is. And it turns out from an instruction point of view, I can either give you that or I don't. I can't really do an awful lot with it. I suppose I could do a diagram and have you recognize how much of a wavelength that was. But we never practiced that in homework, so I probably wouldn't do it. You know, I feel like, man, I like you to practice either in previous tests or in homeworks, at least the skeleton of what we're doing. I'll throw curves in there, but I'm not going to do a completely different skill like that. So we did those guys, and then we came along, and we got to this point here, really, last time. And what we're doing now is we're saying, okay, so this is our system. We have this oscillator, and you know, I'd like to go beyond knowing what its y displacement is. I'd like to know what its instantaneous velocity is. It's still going upwards, but what's its v? And you know what? I'd like to know what its acceleration is. Can you tell me from your knowledge of General Physics 1? So, no, before that. What direction is the acceleration on this particle at this instant? It's downwards, isn't it? How do you know it's down?
Because it's going to turn around.
Well, it's slowing down. Yeah, it's going to turn around. It's slowing down before it stops and turns around. Yeah. So remember we're talking about that oscillator. We're talking about that oscillator. And so we have, well, y is equal to, it's a partial derivative because it depends upon x and t, but we're only going to mess with the time. We differentiate with respect to time, so we get, what did we say? We said y was equal to, what was it? A sine kx minus omega t. Sorry, I wish I could tell you that this was deliberately left out, but it's just in the conversions, for some reason it drops some things. And so then we differentiate it, and we get minus omega a cosine kx minus omega t. And if you want the acceleration of the thing, what we do, minus omega squared a sine kx minus omega t. So boom, 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 boom. Very nice. It's all the vertical stuff we're talking about. We're not talking about the directional stuff in that direction. We're talking about the vertical stuff. Yeah. Cool. Okay, what is the speed of the wave on a string? Basically, we'll do this in lab class. Not immediately. It's going to be a couple of labs away. And basically, what we say is that V equals the square root of the tension over the mass per unit length. And I kind of pull that out of a hat. Let's see if it makes sense. So the mass per unit length is mu. This mass per unit length is, if you imagine a piece of string, it's how much mass each meter has. That's our mu is equal to, it's measured in kilograms per meter. So it's, if you have big thick rope, it's going to be a bigger mu than little thin rope. And it behaves differently. Big thick rope will have more mass, more inertia. I'd expect the energy traveling down the string to be a bit sluggish. Yeah. And that's if the mass per unit length increases, my velocity decreases. And then the tension is the elasticity. It's how quickly you pull back to the equilibrium position. And just like a stiff spring has a higher frequency than a small string, a stiff spring, a tense piece of string would be whipped back through the equilibrium position more quickly, which means that the wave's traveling faster. So tension is on the top. Square root, I wouldn't guess the square root. I wouldn't know about the square root, and that's probably, a more insightful thing. There might be some people who could say, it's obviously a square root, but I can't do that. So for me, all I have to remember is, it depends upon tension, it depends upon mass per unit length, and there's a square root in there. And I can figure the rest out. I did show you the PHET site, did I? Or did I not show you that? Oh, I need to show you that. So let's do that now. Let me just jump out of here. I'm sorry. Let me just jump out of here. I'm going to go to I'm going to do that all later. I'm going to go here. I'm going to type in PHET when you get home. And basically, PHET simulations are done by the University of Colorado. And there's chemistry, biology, there's math, and there's also physics simulations. And if you get your physics simulations and you look down this list here, there's motion, sound, work and energy, heat thermal, quantum phenomenon, and the like. And let's go to our sound waves. And if I look on this, there's this little guy at the bottom. So I basically will double click on that. You can download it to your computer if you want, but you can also do it on just by clicking on it. It's theoretical. It's kind of like calculated, but means it doesn't suffer from the normal issues about a realistic thing where it sags in the middle and it's hard to see. You've got a lot of control over this. What can I play with? I can have a manual, an oscillatory, or a pulse type of motion. And then at the fixed end, I can have a fixed end or a loose end, or no end if I like. Goes out of a window. But let's say we have a fixed end. And I can mess with damping. I can make it lots of damping or no damping. And I can make it high tension, meaning high speed, or low tension, meaning low speed. And the mistake that I used to make with these things is I just like play with everything at once and never really got that much out of it. And what I learned is that if you treat it like an experiment,
and you only change one thing at once, and you're thoughtful about it, you can actually get an awful lot out of these things. You can add rulers, you can add a timer, you can add a reference line. I mean, you can make it as quantitative as you want. There's a big discussion going on in physics about, do you really need to go to a room to do experiments? And most people say, of course you do. And I think I feel that way. If you never pick up a ruler, then you've not really done, a lab. But having picked up a ruler, can you only do lab in a lab room? I don't think so. I think you can learn a lot from something like this. As long as you treat it with the respect of, it's not a video game. Well, it's not a haphazard video game, but you control things carefully. I want to show you two things. And it's to do with the end, loose end or fixed end. So let's do a pulse. Got a little machine here. When I click on it, I get a pulse. I've got a fair amount of tension, of damping on there. I'm going to loosen that up a bit. The disadvantage is it will start bouncing backwards and backwards and backwards. I want to slow that down a little bit, just so that we can see it a bit more. So slow that down a little bit. Oh man, I guess it's only low. Oh, that's interesting. Low or high, that's interesting. Boom. So there's my pulse. Okay, I'm going to get rid of all the tension, all the damping, because now it's not even making it to the end. There's my pulse. And I guess the end. So let's just, I need to clear that up, restart it. Here's my pulse. It's a crest. It's traveling down my piece of string. It hits the loose end, and it becomes a trough. Okay? Let's make this a loose end. Let's start again. Crest. Traveling down a piece of string, reaches the end, and comes back as a crest. And that's just not a computer glitch. That's real. If you go to a swimming pool and you push a crest of water towards the wall, it comes back as a crest. A wave goes and a wave comes. Yeah. If you were on a waterbed or something like that and you bounced on it so that a crest of water underneath the membrane of the waterbed mattress went to the edge, it would come back as a hole. It's the weirdest thing. If I have a piece of if I have Slinky, the spring, and I hold it at the end, what goes as a crest pulse will come back as a trough. If I tie a piece of string to that end and hold the string so it's a loose end, the end of the string can move like that, end of the spring can move like that. What goes as a crest comes back as a crest. If I have a coaxial cable and I'm sending an electrical signal down and I have mismatch between the resistance of the connector and the wire so that the signal sees a difference in resistivity as it goes through the connector, I will get reflection. And depending upon whether the wire is more resistant than the connector or the connector is more resistant than the wire, when it bounces back, it's going to be a crest or a trough. What was a crest will go back as a crest, or it will go back as a trough. I can have light. When you look at yourself in a plane of glass, if you go to a shop which is basically closed down, and you're in the street where you're lit, and you look at yourself carefully, you will see two images of yourself. One is from the front surface of the glass, and the other one is from the back surface of the glass. And it turns out, although they look identical, it turns out that one from the front will, the actual photons will be phase shifted upon reflection, and the ones from the back will not. Now, it looks identical, so who cares? What matters is when you bounce back, you're affecting the signal that's coming in completely different ways. If you bounce back as a crest, you add to crests and you subtract from troughs. If you bounce back as a trough, you add to troughs and you subtract from crests. So it messes with your signal in different ways. So this is not just it's not just to do with pieces of string. It's fundamentally very important. And it's real. How do we mathematically describe this? What we say is, when we have this fixed end and we oscillate it. What we say is that you suddenly go from a crest to a trough. That's like jumping half a wavelength ahead or half a wavelength back. That's really significant. Mathematically, if my journey for this wave is not just down the wire, but down the wire and bouncing back, I got to take into account that phase jump. Okay? So, all I need you to know at this stage is, let's go back here. And it works. Okay. Let's go back here. Yeah, I'm going to have to go to it. Yeah. All I need you to know at this stage is that there is this phase jump effect. And we say, consider a traveling wave that encounters a change in the medium. If the medium termination is fixed, then reflected wave is anti-phase. That means, something happened there. Oh yeah, I've got rid of my pen. That means that it's jumped from a crest immediately to a trough. And so that's a pi phase jump, if you like. Yep. And if it's a loose end, mechanically, if it can slide up and down, then there's no pi phase jump. It's a crest and it's a crest. It's a crest and it comes back as a crest. And goes on the way. Mathematically, they're different. And I don't get fractions. I get a half wave jump on half wavelength phase jump or no phase jump. Or I get, let's say it in other words, I get half wavelength phase jump or no phase jump. I get pi radians phase jump or no phase jump. I get 180 degrees phase jump or no phase jump. 3 different ways of saying the same thing. Okay? So, and I need to be able to keep track of that, especially we're going to get to light and we need to keep track of that. It doesn't even have to be a fixed end. If you are going to send your wave into something which is more inertia filled, a thicker rope, then you will get reflection. You get reflection whenever there's a difference. And the reflection, well, that is sluggish, so it acts like a fixed end because it's sluggish. You're going into something that's more sluggish. And so what was a crest comes back as a trough. Yeah?
What returns, will that be a lower amplitude or will it be the same amplitude?
Oh, it'd be a lower amplitude, yeah. Because the amplitude is reflective of the energy. Right. And so you're only getting a little bit back. And that's the problem with my diagram. I'm showing this thing has been, you know, this should be not quite as big as that, and this should be smaller still, you know. Oh, the two of these should, you know, the energy of the two of these should add up. Yeah. So good point. And then for the other one, if you're going into a lighter string, for example, so you're going in a heavy string, going to a lighter string, it's like having an unfixed end, and so you do get reflection because there's a difference in the two media, but the reflection comes back without a phase jump. And that's what I need you to know. I need you to know that conceptual difference. We'll get to the math, you know, down the road. But not now. So, this next little bit is us playing games. And I think it's useful every now and then to show you the mathematics of the derivations so you can go through it. But I guess my sense is I don't have time really to dwell on it. So what I did was I took what's in the book and I kind of extended it. Sometimes the book tends to make jumps. I'm never going to ask you to repeat this, but I don't think it's necessarily a bad thing for you to go through and just square it off with yourself. I mean, basically you're just saying, well, I know that spring potential energy is a half K times the amplitude, times the displacement squared. I know that from Physics 1 mechanics. And then you start substituting and you say, well, hold on. You know, I can substitute in for K. I know that K equals M times omega squared. And then I can say, well, I know that my mass per unit length is M divided by X, so I can substitute that in. And so on. I guide you through it. You substitute in the wave expression for your Y, because you know an equation for Y. and so on. You go through it, and you end up with this expression here, which is, until you get to this page, and then you say, well, okay, I have an expression which gives me the energy I have in a little bit of length for the wave. So here's a piece of string, a little bit of length. How much energy is in that little bit of length? That expression tells you that, which is kind of amazing, really. But let's try and standardize things. So we're not going to talk about a little bit of length. I want to talk about one wavelength. That seems like a reasonable standard length to talk about. And so I integrate this with respect to the wavelength. And this is another thing. So there's an identity there that we've done. And you wouldn't just, I don't think most people would just catch it out of the air. They did it in calculus, or they did it in probably trig. And you'd have to look back at your book. I had to look back at my book to say, where's that coming from? So I don't need you to know that in detail. I want you to be comfortable with the answer. And in fact, you don't have to remember this. When we had the equation sheet, it was on the equation sheet. But frankly, these days, without an equation sheet, it's something that I think that I'd like you to be able to interpret. So I'm not above giving you this equation and saying, oh yeah, the potential energy inside one wavelength of string is given by a quarter mu omega squared a squared lambda. And then I might turn around and say, so how does mu lambda go with lambda? And you say, well, it's linear.
Yeah. Because if all these other things are constant, then if lambda doubles, your mu lambda doubles. It's linear. How does mu lambda go with amplitude? Oh, well, then it's a squared relationship. If I double my amplitude, I 4 times my energy. So I'll gladly give you the equation, but then I want you to interpret it. So to do that, you've got to know some math, and you've got to know what the letters stand for. So I don't think you can just like put a line through this section and say, I'll never look at it again. I think you have to say, I don't really need to remember the equation, but I need to know what these letters stand for. Mu is the mass per unit length. You know. Does that make sense? And if we do the same thing for kinetic energy, we get the same equation. It's actually, this is the, because the energy is going backwards and forwards between kinetic and potential. I mean, that's what happens with these energies. And if I say my mechanical energy in one wavelength is equal to my potential energy in one wavelength plus my kinetic energy in one wavelength, then I get 1/2 this guy. And again, it's like, I don't want you to remember it. If I do anything, I'm going to give you that equation and say, hey, how are these two guys related? Okay. This next bit is a bit like, sometimes I think the book kind of like develops things and makes new equations that you could readily get. I mean, power is always, the energy divided by the time interval. And so if you have that amount of power and the time interval for one wavelength is 1 period, then you can say, well, hold on, this is lambda over t, and lambda over the period is the velocity of the wave. So they make this new equation, but really it's just applying a standard equation to what we just had. So I'm not sure. It's new, really, It's a bit like having a whole chapter saying, we've just done, how many yards there are from here to downtown. That was one chapter. And now we have another section where we say, and by the way, here's a derivation that shows you how many inches there are. But I know there are 12 inches, I don't know 36 inches in a yard, so I don't need that bit. It looks like it's something completely different, but it's just this little step on. And that leads us to the wave equation. And we don't do that's a terminal for us. We don't do anything with it. If you do mechanics, you'll see this again. If you do electrical engineering, you'll see this again. But I'm just going to show you the form of it. There's a thing called a linear wave equation, which basically relates your
basically your d2y by dx squared to your d2y by dt squared, and there's a constant in front which is 1 over the velocity squared. And it pulls out of a hat. You've seen it. I will not ask you about it. I'm going to, when we get to EM theory, I'm going to refer back to this equation. I'm going to show you a comparison, but that's all I need to do. Okay? Okay. So there we have it. I'm going to stop my session there.